This problem is interesting because there are a lot of levels to it. At a minimum, everyone should be able to come up with at least one working solution. You don't need any prerequisite knowledge in order to solve this problem. And then from there, you should be able to hold the problem in your hand and think about it from multiple angles and see all sorts of different approaches. And then when you have those different approaches, you should be able to weigh the trade-offs between them when it comes to time, space, and overall design. Now, before I walk you through my thought process, I want to give you a chance to work through it so that you can see what I'm talking about. So hit pause now and give it a shot on your own. Any programming language is fine. So I assume you've taken a shot at solving the problem on your own. Here's how I would approach it. So I'm noticing that there are two main elements that we need to consider. One is right here. We have a count. And then two, we have the description or condition for that count. This is one step away from a one, so we count it. This is 2 steps away, so we count these two. We don't count the last one. Here, same thing. This is 1 step away, this is 2 steps away, and we don't count the first 0. So I'm noticing that the question talks about zeros in the aggregate, but we're going to need to examine each 0 individually, so it makes more sense to think about it from this way. And of course, we need to ask this repeatedly, so I'll add for each 0 in the input. And then here I'm noticing we're getting the structure of a possible solution for free. So I'm just going to add the other element that we haven't included, the count. So that count will start at 0. And then when we see a valid 0 that passes our condition, we increment. And then finally, we just return that count. So I like the overall structure here, but I have some uncertainty around this line right here. I want to figure out how exactly that's going to work. And at this point, I just want to think about it as simply as possible. We just want to get it to work. I don't care about optimizations at this point. So let's try to conceptualize what's happening. We're going to look through each character in our string. So we're going through, looking through, and then let's imagine that we hit a 0, because that's where we're going to try to answer this question. So this dot will represent the index we're at. And then if we want to answer this question, we can quite literally just look n spots to the right and n spots to the left. And if we see any ones in any of those slots, then we'll increment our count. And I'm quite confident we can execute this. This is just a straightforward checking of the neighbors n to the left and n to the right. So now that we're confident that this works and we could execute this in code, we want to think about trade-offs, how this might compare against other possible approaches. So I think conceptually it's unlikely we're going to be able to beat this one. This is the most obvious one we came up with, and it flows quite literally from the problem statement. But what about time and space? So when we look at this picture, we can tell that when we come to a 0, we're going to have to look n to the left and n to the right. So we're going to have to look at 2n elements for each 0. So at each 0, we're going to have to do 2n checks. And then our string could be full of zeros. So the length of our string, I'm just going to call it L, would be the maximum amount of work we could do. So this would be our performance. We could simplify this down to O of L times n. There's no way to avoid the length of the string because we're going to have to examine every 0 at least once. But my question is whether we can avoid this n part of our time complexity. So that's one thing to consider, and that would motivate how I would look at other potential approaches. So that would be for time. And then for space, we're doing pretty good here. We're not using any extra space, so we're O of 1. So the thing here is, I think conceptually, this is likely the clearest approach, but we have some potential room for improvement when it comes to our time. When trying to optimize algorithms, I often use a framework where I imagine that I have perfect information about the problem. So what perfect information would help us optimize this n right here? So this comes up when we're trying to answer the question, is this 0 within n steps of a 1? So if we had perfect information about the ones that are closest to this 0, then we could just measure the distance between this 0 and the ones on either side, if there are any. And if we manage to do that, then our algorithm would be time O of L times 2, because we would have to measure two distances between the 0 and potentially one on this side and potentially one on the left side, which would simplify to O of L, where L is the length of the string. Now, if we did have perfect information on all of the ones, we would need to store that somewhere. So naively, if we assume that we're going to store the location of all of the ones, in the worst case, we have all ones, then for space, we would be using O of L space. Let's assume that we have all the information. We've stored all of the ones that appear in our input. So you could think of an input like this. We have 3 ones. We have a 1 at index 0, at index 3, and at index 6. And so let's imagine that we stored all of these ones in an array. How could we use this information to answer this question, is this 0 valid, faster? So let's say that we were examining the first 0 right here at index 1. We have in the array the information of the 2 ones that are closest at 0 and index 3. And we can just look at the distance between the index here and 0 and 3. And then we can check and see if that value is less than or equal to n. But we need to make sure that at this point, we only consider these 2 elements in the array. We want to make sure that we don't have to go search through the array, otherwise that will be slow and we won't get any benefit. So one thing we could do is first we'll consider the first pair within our ones array, which represent this first interval. And then when we get to index 3, we can see that it's at the end of our interval, our current interval. And so we need to move on and look at the next pair in the array. And then when we're looking at these zeros, we can only concern ourselves with 3 and 6. We don't need to search through the array to find where the nearest ones are. From this analysis, I'm convinced that we can get this performance. Yeah, we're going to store all the ones and have O of L space, but then once we're looking at a 0, we can just compute the distance between this index and the 2 ones that are closest through just 2 subtraction operations. The obvious next question is whether we can improve on the space figure from O of L down to O of 1. Now, when we came up with this approach, we asked ourselves, how could perfect information about all of the ones help us get a faster algorithm? And it did help, but at the expense of space. Now we want to think about a different question, is can we cut any information out? Is there any information that we're storing that we're not using? So let's think about what's happening in this previous approach. So we're storing all the ones, and each pair of ones represents a sort of interval. So very similar to the diagram above, but we can think of our input as this series of intervals. So for example, right here, when we look at a 0, we want to know how far this 0 is from this side to this side, because these are the ones. And is this distance less than or equal to n? And we just keep going along trying to ask that question. But the thing to notice is that we're storing information for all of the intervals. But at this point, when we're looking at a 0, like right here, we only care about the interval that the 0 is in. We don't care about these at this moment. Same thing here, when we're looking at this 0, we don't care about this interval, we don't care about this interval. And then if we're looking at a 0 right here, we don't care about these, so we don't need to store them. So if we could figure out a way to store just one interval at a time, then we would get O of 1 space, and we would get O of L time, the best of both worlds. So let's think about how this could work. So at the very beginning, we need to define our first interval, so we can find the first one and then the next one, and that will create our interval. And then when we come to the end of the interval, this will be the beginning of the next one, and then we just go along and look for the next one, and then that will be the next interval. And then when we are iterating and iterating and we see the end of the interval, then we need to go create the new one. And so we can do this in O of length time, because we're only going to examine each index one time when we're creating these intervals. So for example, if you had something like 1, 0, 0, 0, 0 all the way, then we would only create one single interval. We're not gonna like go back and revisit indices when we create these intervals. So this can be done in O of length time. And so based on this analysis, I'm confident that we can get time O of L and space O of 1. So now we have our three strategies. The first one was the most obvious one, but it's a brute force strategy that's very slow. The second strategy is faster, but at the expense of space, and we got there by storing all of the ones. And then in our third strategy, we got a performant approach, and we got that by storing just a single pair of ones. In everyday situations where I might care most about clarity, strategy 1 might make the most sense because it's the simplest one. If I'm in a situation where performance matters a great deal, then strategy 3 would be the obvious choice. And then strategy 2 would be somewhere in the middle. Coming up with these strategies and seeing the problem from different angles is the hard part. A separate and relatively easier skill is being able to implement them cleanly in code. So if you haven't yet, hit pause now and see if you can implement all three strategies before I show you my process. I'll start with the first one, and I'll be doing these in JavaScript, but you should be able to understand what I'm doing if you're familiar with any programming language. So first, I want to try to get this outline into our editor. So the only part we really need to work out is this section at 11 and 12. And so here's where the picture is pretty useful. Given that we're at a 0, we need to look n spots left and right, but we need to do that one at a time. So we need to go 1 spot to the left and right, 2 spots to the left and right, all the way to n spots to the left and right. So we need to have some value that starts at 1 and then goes all the way to n. So I'll get that set up. And because we're moving from a fixed index, I'll call this value an offset. So the index to the left of I will be I minus the offset, and then the index to the right of I will be I plus the offset. So we want to access those characters, and then we want to see if there's a 1 there in either of those spots. So I'm going to put this in an if statement. So we have these two checks. Is there a 1 to the left or the right? And then we'll wrap that in an if statement. And then if we do see a 1, then we know this 0 is valid. We can increment our count, and then we can stop looking for this 0 so that we can break out of this loop. So there's no need for the comment right here, but I'll leave the comment at line 11 because it does capture what's happening in this block of code. If you happen to be using a language where you might access invalid or incorrect indices at line 13, then you could just add a check to make sure that the indices are valid and correct. In JavaScript, it doesn't matter though, so I left that out just to keep it simple. So now we'll implement the store all ones strategy, and the starting point will be the same. We're gonna work from this outline. So I already have this in code form in my editor. Now I wanna focus on what makes this strategy different than the others. And the main one, of course, is we wanna store all of the ones. So let me incorporate that into our code. So at line 9, I'm adding a note, store all ones. And then once we have all of the ones stored, we're going to go through character by character and look at the distance between each 0 and the left side of the interval and the right side of the current interval. So broadly, the section where we are asking whether this 0 is within n steps of a 1, that will broadly be the same. We'll do 2 subtraction operations. So I'll leave that for now. But the main thing that's different is at each point, we need to consider whether we've reached the end of a current interval, because that means we need to shift over to the next pair in the array and get set up for the next interval. So I'm going to add a note so that we handle that logic. So here I'll say, are we at the end of an interval? And if so, then we should move on to the next interval. So now we have to figure out how to store all of the ones. In the example right here, we had a neat situation where all of the zeros were surrounded by ones, but that's not always going to be the case. So if you have an input like 0, 0, 1, you obviously have a 1 on the right side, so you could draw the right side of the interval. But how are you going to model the left side? So the right side has a 1 at index 2, but what value are you going to put for this question mark? So the natural instinct is, at least for me, was to put undefined. So on the left side, we have undefined because the thinking is there's no 1 on the left side, and on the right side, we have a 1 at index 2. And this would work fine if you see undefined on the left, then you know that there's no way you can have a 1 within n steps because no 1 exists. But this is a little bit frustrating because what we're doing is we're going to compute the distance between any zeros in the interval in the right side and the left side, but you can't do math with undefined. So I thought about it a little bit more and I came up with a different idea. And the picture looks more like this. We have 2 on the right, but then on the left, we just have an arrow that goes on forever. And the idea is that there are no 1s on the left. You could go on forever and never reach 1. So the 1 on the left is infinitely far away or unreachable. And you can model this with negative infinity. It's infinity away. And when you have a number representing this, then you can use the same logic to compute the distance between any index and negative infinity. That will be infinity. And there's no way infinity will be less than or equal to n. So this is a neat way to represent these types of cases. So with this little trick, we can model any situation. We just need to put a negative infinity at the beginning of our array, and then we can put a positive infinity at the end of the array in case we have the same situation at the end. So I'm going to break this up into steps. Our first step is we want to add negative infinity, and this is to model the left side of the first interval. Then we'll store all the ones, and then once we're done, we'll model the right side of the last interval with positive infinity. So let's create our array. I'll call it 1 indices, and we want it to have negative infinity. The next step is we'll store all the ones. I'll just go through, and wherever I see a 1, I'll push that index to our array. And then finally, we'll model the right side of the last interval with positive infinity. So we'll just push positive infinity to the end. So our 1 indices array looks great, but before we go ahead and check the zeros and update the intervals, we need to set up our first interval. So set up first interval, And remember, our intervals are modeled by pairs within the one indices array. So at the beginning, we want the elements at indices 0 and 1, and then 1 and 2, and so on. So we need to somehow model these two values. So since these will be indices within the one indices array, I'm going to name this one indices left index, and this will represent the left side of our interval. So, and of course that'll be 0, and then one indices right index will be 1, and then later to update the interval, we'll just increment both of these. So that sets up our first interval. And then the logic for doing this, we can add it right away. We're just gonna bump this up, and then we would also bump up the right index. So that would allow us to move to the next pair within the one indices array. So now let's think about how would we know if we're at the end of an interval. Well, we want to get something that has to do with the one indices right index, but this is just an index in the one indices array. So we need to go index one indices, and now this represents an index in our input where we have a 1, which represents the right side of our interval. So if I is equal to this value, that means we're at the end of an interval. So if I equals this, then we know we need to go ahead and move on to the next interval. So I'll move this logic to inside of this statement. And then this part is relatively simple. We want to check the left side and the right side. So I'll create two variables to simplify this. So has one on left and has one on right. I'll work that out later. And then if we have either of those, or has one on right, then we'll increment our count. So now we just need to fill out these values. So we want to measure the distance between the current 0, which is I, and the left side of the interval, which will be one indices, one indices left index. And if that distance is less than or equal to n, then we're good. And then here, we want to look at the distance between the right side and I. So we can do one indices right index minus I. And if that's less than or equal to n, then we're also good. And so that's it for this implementation. The coding is relatively straightforward, but there is a little bit of nuance in how you model the ones. We had to do the negative infinity thing and infinity at the end. You could use undefined, but it would make the code a little bit more complicated, but that would definitely work. And then in the case of actually using the one indices array, it was a little bit tricky because we had to keep track of indices in the one indices array and increment those, which made accessing values a little bit tricky. But if you take some time to kind of think about what's happening, it should make sense. So finally, we'll implement the last strategy, which is our performant one, where we store a single pair of ones. And this will actually be surprisingly straightforward because we've already worked out a lot of the issues in implementing our previous approach where we stored all the ones. So a lot of the things that we saw in that approach we can borrow, and that's because the way we're modeling the intervals is exactly the same. So for example, the thing with negative infinity and positive infinity, we can borrow that idea. The only difference is that we're not going to store all the intervals. We're just going to store one, and we'll see how that changes our code. So we're not going to store all the ones, but we do need to do some work to set up the first interval. So I'll leave that as our first task. And then once we see a 0, we need to check the distance between the 0 and the left side and the right side of the interval. So I'll make a note, check distance from left and right sides of interval. And then the last thing we have to do, which is really similar to the approach where we stored all the ones, is we need to update the interval when we get to the end of the current one. So I'll add a note here. Are we at the end of our interval? And if we are, then we have to move on to the next interval. We know from the previous strategy that we want to represent the left side of the first interval with negative infinity. And then the right side of the first interval should be the index of the first one in the string. Now previously we could just pull that from an array, but we're not storing that information, so we have to compute it somehow. So knowing that, I'm just going to delay that work for now. I'm just going to assume that we have a function that will do that for us. And I'll call it getIndex of next one. And since we haven't implemented it yet, I'll just add a reminder as a prefix. So we'll give this function our string, and then we also have to pass in where we want to start looking for the first one. And since we're at the very beginning, that'll be index 0. So this will give us the position of the next one in our input, and will represent the right side of our first interval. And then of course, this will be the left side. So I'll call this left one, and I'll call this right one. And that's it for setting up our first interval. So now that we have these two values, left one and right one, we can answer the question at line 15 by computing the distance between the 0 and each side. So I'll go ahead and add that logic now. And that's it for this section. Our next major task is to figure out this logic. So we know we'll be at the end of the interval when we hit the right side. So we can just do a quick check for I and see if it's equal to our right one variable. Now that we know we're at the end, we just need to update to the next interval. And here's where our picture can be pretty useful again. Let's say we're at the end of the first interval and we want to set up the next one. So at this point, I'm noticing that the two intervals overlap, and more specifically, the end of this interval is the beginning of the first one. And so if we want to set up the left side of the next interval, we can just use our current index, which is I. And then to get the right side of the next interval, we just need to find the next one, and we can use our function getIndex of next one to do that. So that makes the left side really simple. All we have to do is set left one equal to I, and then for the new right one, we'll just have to use our function to compute that. So we'll grab our function and we pass in our string, and then the place where we should start looking for the next one. We know we already have a 1 at index I, so we can't start looking there because we just get back I. So we need to start at I plus 1. The last step is just to implement this function. So I'll get rid of the to-do prefix and we'll write the code below. So we want to start looking for a 1 starting at I, and then we'll keep incrementing index of next one until we see a 1. But if we go off the end of the array and we don't see a 1, then we'll model that with positive infinity. And that's it for the performant approach. If you reflect on what we did, I think the most important part was coming up with these diagrams. Because if you can't generate these ideas, it doesn't matter how good you are at the mechanical aspects of programming. Once you fully flesh out your ideas, implementation should be very straightforward, with a few minor design decisions here and there, like the infinity thing.